So in this week's AI seminar, we're joined by Ruolin Li. She's a Gabilan Assistant Professor in USC's Department of Civil and Environmental Engineering. Her research focuses on active control and management of autonomous vehicles in mixed autonomy environments, using game theory, multi-agent systems, and optimization to enhance the societal benefits of intelligent transportation systems, particularly more adaptive and cooperative mobility networks. Before USC, Ruolin was a postdoc in the Department of Aeronautics and Astronautics at Stanford University, and she earned her PhD and MS in mechanical engineering from UC Berkeley. You can post any questions you have during the talk in the chat, and I'll try and raise them in the room, or anyone in the room can just raise their hand and ask questions during the talk too. With that, I'll hand it over. So, thank you.
Thank you, Eric. Thank you, everyone, for attending my talk. And I think it's a very good chance for me to introduce myself to you and also my research. So today, the talk title is Harnessing Autonomous Vehicles for Smarter Traffic Management. And I'm sure we're quite familiar with the autonomous vehicles. And it's no longer the wildest dream that we see autonomous vehicles navigating our streets. For example, we do see these bunch of Waymo vehicles traveling around, providing services, and other kinds of robo-taxis. And looking ahead, we're not just talking about isolated deployment of only a very small penetration rate of autonomous vehicles, but we do expect that penetration rate of autonomous vehicles to increase in the near future. At least it is the current situation with Los Angeles. We see more and more Waymo vehicles traveling around. And we do expect that this mixed autonomy environment, where a bunch of autonomous vehicles coexist with human-driven vehicles, which we call it mixed autonomy, to persist at least for decades. And in the United States alone, the AV market is projected to cross $1 trillion by 2033. And this exponential growth reflects not only technological advancements, but also increasing public and private investment, commercial interest, and societal readiness. However, today, autonomous vehicles still make up a rather small fraction of the vehicles on the road, and an even smaller fraction of travelers' mode choices. And this can be very challenging when it's only a small penetration rate of autonomous vehicles. For example, because these autonomous vehicles, they need to travel around the human-driven vehicles. And we all know human drivers, as we all are, can be very spontaneous. So that poses a much bigger uncertainty and challenge, not only to the efficiency, but also to the safety of this technology of autonomous vehicles. Compared to the future, when we do expect a certain bar of the penetration rate of vehicles to be crossed, let's say 50%, and then in that case, we would have a much easier environment compared to the current one, because in that case, we have more controllable components in the environment. So, and we expect a decrease in the marginal cost for deployment of these autonomous vehicle technology, as well as a bigger marginal benefit for the deployment of these autonomous vehicle technology. So one of the key challenges that we face isn't just put more autonomous vehicles there, but it's more about finding the right balance and eventually pave the path among goals of different stakeholders. For example, autonomous vehicles companies optimizing their profit, cities managing congestion and expecting less cost and more revenue, and individual users valuing safety or travel time. So to truly explore the potential of these autonomous vehicles, we need to think strategically about how to scale up their deployment in a sustainable and coordinated way, especially as they navigate and interact within mixed autonomy environments, all kinds of road users like human drivers or pedestrians, which should be the case for at least several decades into the future. Therefore, my research group, which was just established in last August at USC, we try to escalate the potential benefit of population of autonomous vehicles in the intelligent transportation systems. And in the meanwhile, we also want to re-engineer the current transportation systems for the seamless integration for autonomous vehicles. And the focus of our group is on the interaction of autonomous agents to the human drivers and the control components in the system. And today, I'd like to show a series of ongoing projects in my lab, which is focusing on the interactive mixed autonomy across all kinds of geometries in the traffic network. And this interaction, we see it across almost every in theoretic scenario in the traffic system, like roundabouts, toll lane, ramps. And many of these interactions, particularly in the mixed autonomy scenario, raise the same core question: how do agents interact? How do we model the behavior? And is it possible that we can influence it for better outcomes? And these are the kinds of questions my lab that is currently deep engaged with through both ongoing and past research. And today I'm going to use several of the scenarios as examples to illustrate the interaction which we care about. So for the first, I'd like to show you some behavior of human drivers. So this is the very notorious last-second lane divers. And this behavior is the very crazy last-second axis. Even though I call them crazy, sometimes I'm one of them. So very obvious, these behavior, they're very dangerous to themselves, but also they're very dangerous for the vehicles that are surrounding them. Not only about the efficiency, but also the safety, because they create a big disturbance. And the underlying reason for such crazy behavior is actually quite rational. So the underlying reason is that human drivers are selfish. By selfish, I mean they only care about their own utility or their own best interest. And they ignore their impact of their behavior on other vehicles, not even the system. So our conjecture is that with autonomous vehicles, which are more controllable, less spontaneous, we could leverage these autonomous vehicles. But one thing that we need to make sure is, because these human drivers, they're selfish. So if we do leverage these autonomous vehicles to do some altruistic behavior, then naturally these selfish human-driven vehicles should take advantage of these. So therefore, in terms of designing the control, we need to consider this interaction, this key interaction component into our design. So today, I'm going to use the first example, which is a recent work in collaboration with my very talented students on designing the control involving the weaving ramps, which is a very notorious bottleneck that we can see in our daily life. So let's first decipher how human drivers would behave in such a complex weaving ramp. So all the arrows would show the very complex interactive vehicle movements in this weaving ramp zone. And you see that every circled movement indicates a certain merging or traversing movement with other parties of vehicles. And if we kind of decompose the complex vehicle interactions, we see that actually the movements that are not colored in red, those are the movements that are totally goal-driven, which means, for example, if a vehicle says, I'm going to exit this ramp, then he or she would exit that ramp. You cannot tell he or she like, okay, wait, and you can exit for the next ramp. But the behavior that is indicated by the right, these are the behavior that are actually results from decision-making. So this decision-making behavior is something that we care about because we can potentially change them by configure autonomous vehicles. And we actually indicate the specific behavior that are colored by red to steadfast behavior or bypassing behavior. So steadfast behavior is that these vehicles that are originally traveling along lane 1, they see this potential merging and traversing and complex interaction in the very head, and they choose to, okay, I'd either slow down or I'll take a risk So they'll just stay on the current lane. So indicated by the blue trace, we call these vehicles steadfast vehicles. And another portion of vehicles, or the other portion of vehicles that are originally traveling along lane 1, they could just say like, okay, I don't want the very complex interaction and the very complex merging behavior with the vehicles ahead. So what I will do is I will switch to a neighboring lane, which is lane 2 in this case, to avoid the complex merging. But of course, if you have vehicles that are originally traveling along lane 2, they have to inevitably merge with the vehicles that are traveling along lane 2. And the thing that we care about is it possible that we could predict how many vehicles would choose to bypass and how many vehicles would choose to steadfast given any Vivian rep that we see in our daily life? So if we can do that, then perhaps we can, change our control and design our control to influence that collective behavior to do us some good. So all in all, in the end, so we chose a model-based method where we use some game theory concepts. So the key assumption here is that we assume these vehicles, they're selfish, they want to minimize their cost. And their cost is essentially the delay and the two different options. So each of the agent would evaluate whether it's going to be more costly to stay steadfast or it's going to be more costly to bypass. And they will always choose the option that can minimize their evaluated cost. And we will investigate their aggregate behavior in terms of the equilibrium, which means we will only see when everything gets static and we say, for example, we can predict how many vehicles would choose to bypass and how many vehicles would choose to stay steadfast. And the essential thing is like we need to design what's the right formula for these costs that they actually evaluate. So essentially, here is the result after many trials of iterative design. The essential thing is the delay should be decomposed into two parts. One part is related to the traversing behavior where different parties need to use one segment of lane simultaneously for a period of time. And another term is the merging cost, which is when two parties of vehicles with different speed, they need to kind of merge and travel for the same segment of the lane. And the design process is actually an iterative one, which means we need to intuitively, or from the physical sense, we need to propose the right formula that we think, and then we need to calibrate and validate them with data, either collected from simulation or from the real world. And at the moment, when we have the right calibration result and the validation result, we know those are the right model that we are looking for. So luckily, eventually we have our right model, and the model prediction are shown on the right. So basically, the red ones are the model prediction, and the yellow ones are the true data that we consider are true from this macroscopic simulator. So here, any simulator would work, but here we use the SUMO, which is a commonly received simulator in traffic. And as you can see, our model, even though it's linear, but it can predict the nonlinear behavior of such bypassing and steadfast behavior in terms of the macroscopic level.
Do you account for sort of the human risk aversion in these sorts of models? So you might say, or you're about to talk about that.
I'm not, but that's a good question to answer here. That's a very good question. So the thing is, right now, I do consider the macroscopic, which means I consider the aggregate impact. So let's say if 20 of them are risk averse, those tendency would be reflected on the parameters C1T, C1M, C2T, gamma, sigma, those kind of parameters that are lying in the cost model itself. So it should be reflected in the calibration process. Does it?
Yes, thank you.
And then, so all in all, the model is a very good model in terms that every time we require very few parameters. Actually, it's a single digit number of parameters to calibrate from the data. And the model itself only requires flow information. So given a Vivian ramp, the only information that you need to feed into the model and filter in the autonomous vehicles are the flow information on different lanes, or exit vehicles, or entering vehicles. And the linear structure of the cost itself can predict the nonlinear behavior model. And theoretically, we can guarantee that it always exists and it is unique. So it guarantees you the practicality in an uncertain Vivian ramp that you see. And the next question that we want to ask is, okay, right now we can model that, but is it like reasonable enough that we need to leverage some control? Because controls are usually not that, it's usually expensive, right? So we need to compare that whether there is this gap between the selfish behavior that is naturally happening versus the socially optimal behavior that we actually expect. So here we compare the socially optimal behavior and the selfish behavior. As you can see, for most of the cases, there is usually a gap, and this is only from one of the experiments. So for other experiments, this gap can become larger in a reverse direction, but usually the selfish behavior does not align with the socially optimal behavior that we do expect. So that's why we want to propose that, because for such a short time period, it's very hard to motivate human drivers to change their option. For example, like if you don't give them $1 million for such cases, it's very hard for the human drivers to change their decision in a very short time period, considering the very complex scenarios and everything. But if we have a bunch of autonomous vehicles on the roads, let's say 2 out of 10 vehicles are autonomous vehicles, and we could probably give them the dictation that we want these 2 autonomous vehicles to bypass right ahead before the Vivian ramp, to give more space to the complex interaction in the Vivian zone. And right now, we consider in this work that we can dictate the lane choices of these autonomous vehicles on the road by a centralized dictation. And correspondingly, the selfish human drivers, they will correspondingly form this wardrobe equilibrium again by selfishly minimizing their own cost. So eventually what we found out is the very interesting scenario, which is the altruistic autonomous vehicles impact must outweigh the selfish vehicles exploitation. For example, even though you're trying to control these autonomous vehicles in a very dictative way, so they must perform like pure altruistically, you still need enough proportion or penetration rate of these autonomous vehicles.
Could you explain, so you said there's a socially optimal objective, and I understood the equilibrium for the selfish objective, but what is the objective for the socially optimal? Is it sort of like delay over the entire population?
Yeah, that's a good question. So the social delay is actually the sum of all vehicles delay in this scenario. So which means, for example, I think in this case, we have 6 parties of vehicles: exit, entering, bypassing, originally traveling only to, and steadfast vehicles. So the social cost is actually the total delay of all the vehicles that are involved in the Vivian ramp.
And since, I mean, I guess some of these decisions are made, feels like simultaneously, so it might be that as long as one car bypasses, the social delay is improved, but if multiple cars simultaneously try to bypass, it might be, you know, the delay, the social delay might increase. So how do you account for that kind of simultaneity? I mean, in the central authority, obviously, the central authority can choose this, but for humans who might have limited perception.
Mm-hmm. I think that's a good question. So the key assumption here is we do use the equilibrium model, which means I won't say like we focus on the simultaneous, like for example, what's the current lane changing proportion and what's the impact of the current moment, but we do see it as a pattern. For example, like if you repeat this demand, like every time, like at a certain time on the Vivian ramp, and you expect that the stable pattern of the lane changing proportion and its impact. So I'll say it's from a aggregative, static point of view in terms of the eventual game theoretic equilibrium instead of the simultaneous current link-changing behavior. Does that make sense?
Yeah, I think it kind of keeps coming back to this, like, oh, you have a multi-agent simulation, but often you're controlling it with parameters that are an aggregate level. So you're not actually modeling each agent kind of at a very individual level.
Not for now.
Yeah, okay,
Yeah.
I understand, thanks.
So yes, so this is the exploitation behavior. If I stopped there, I forgot. So if the exploitation behavior we do see such exploitation behavior in this Weaving ramp scenario, and we're going to revisit this exploitation behavior in pretty every example that we'll see in the future. And this exploitation is something that we can like intuitively imagine. So let's say for the steadfast bypassing behavior, we use one of the autonomous vehicles indicated by the green one with a heart, and we dictate its link-changing behavior by you need to bypass at the very beginning. And as a human driver, we follow that altruistic vehicle. We see a vacancy show up right immediately before us. So as a selfish behavior, what we want to do is just take that spot. So this is one of the explanation of the macroscopic exploitation behavior that is showing in the model. So for the first example with the Weaving ramp, the eventual claim that I want to make is that we can model these autonomous vehicles as socially aware agents, which means they're more controllable, they can receive more configuration and information, and we can leverage this more controllability to do us some good in terms of the social level. And the second example, I'm going to talk about the on-ramps. So there, what I want to talk about is previously, if we dictate the behavior of autonomous vehicles, sometimes it's not very fair, because that means if you're in our autonomous vehicles, you need to sacrifice something to other human drivers. So the users, they won't be very happy about that. And the AD operators, I don't think they will be very happy about that. So what can we do? So the problem in this case is we want these, as a very brief introduction, we want these autonomous vehicles to drive like these green vehicles, which is they bypass more compared to the vehicles that are originally traveling along lane 1 indicated by the orange color. And so what we propose here is instead of forcing these autonomous vehicles to do their lane change behavior as what we dictate, designed by the socially optimal behavior. So selfish human-driven vehicles, they still minimize their own delay. But these altruistic autonomous vehicles, we give them certain incentivization by designing their decision cost. So the decision cost is actually composed of 2 parts. So one part is their selfish utility, and the second part is to model their negative impact that they impose on other vehicles. And we use a weight, which we call it the altruism level, to weight like how much altruistic these vehicles can be, how much selfish these vehicles can be. So which means we accept this gray zone that these autonomous vehicles, they can do something for themselves, but they just need to consider something for the society. And basically, what we do is like we prove that how many altruistic vehicles and how much altruistic vehicles do you need to decrease the congestion and to optimize the congested scenarios. And we also see that exploitation behavior in this case, because you need to reach a certain bar to make sure that your altruistic behavior can overweigh the selfish behavior that are induced by the rest of the human-driven vehicles. So that's the second part. That's the second example, which is we can not only dictate the lane choices of autonomous vehicles, but we can incentivize these autonomous vehicles. And the third example that I want to use is the very common setting for traffic for autonomous vehicles, that is the routing on networks. So the reason that I want to bring this example is that if we do expect that we can dictate the lane choices or incentivize the lane choices of these autonomous vehicles on the road, and we do have this certain penetration of autonomous vehicles on the road, how can we possibly form them in an effective team to maximize their own benefit? So in the routing scenario, like every vehicle would choose a path to minimize their own delay. And it's a mimic of the shortest path algorithm. And at the equilibrium, every vehicle would reach this equilibrium that is saying like no one has an incentive to change their choice of the path, given other vehicles' choices remain unchanged. And in terms of organizing these autonomous vehicles, human drivers, they usually have a more spontaneous and longer headway. But autonomous vehicles with certain type of control, like according to previous literature as well as experiments, we have shown that these autonomous vehicles can preserve a much shorter headway compared to human-driven vehicles in an organized way, for example, in a platoon. And therefore, because of the shorter headway, and usually the delay related to a road is according to the ratio of the effective flow compared to the capacity of the lane. And we shrink the headway of the autonomous vehicles, which means if we have autonomous vehicles on the road, then we should have a smaller effective flow, or in another way, like we're increasing the lane capacities by using autonomous vehicles. So we do expect that using these autonomous vehicles in platoons, that they should effectively decrease the delay of the roads on the network. And the next question is like, will autonomous vehicles always help? So we prove that for the certain type of networks, by certain type, which means if the networks has only a single origin destination pair, which means all vehicles on the network would travel from a single origin and they choose different paths to reach the single destination, then we can always decrease autonomous vehicles' headway to decrease the social delay of the whole network. However, furthermore, if it's an even simpler type of network, which is the network with parallel links, let's say all the paths, they're parallel, they're not overlapping with each other by the rows, then we can even estimate how much of the impact can you expect from these autonomous vehicles. And this impact should be related to the penetration rate of autonomous vehicles, as well as the certain quantification or representation of autonomous vehicles' headway. However, with more complex networks, for example, the networks with multiple origin destination pairs, so here, even though geometry doesn't seem complex, but it's a complex in a way that we have 3 origin destination pairs, and each origin destination pair, they will share the path and links among them. So the result is, in this case, if you shrink the headway of autonomous vehicles, you can actually increasing the social delay from the right to the left. You're shrinking the headway of these autonomous vehicles, but it's actually increasing the social delay of the whole network. And the underlying reason for that is still selfish vehicles exploitation. So in this case, you can think of if you use, for example, 80% of the autonomous vehicles on a certain route, you want to decrease the delay of that route. But the other human drivers, they spot that change. So what they want to do is they want to make use of that advantage, so they will change their route to that route with more autonomous vehicles. So in the end, the gaming behavior between agents would eventually make the social traffic conditions worse.
So is the intuition here something like you hear like on the radio,
yeah,
there's a delay on this path, so everyone like takes the other path, and then like there's a traffic jam there?
Yeah, that's actually that's a very famous brass paradox in terms of traffic, the literature. So brass paradox was talking about like if you have two cities, A and B, and what they want to do is they want to decrease the congestion between the traffic from A to B. So what they want to do is they want to build a very wide highway, a new very wide highway. And in the end, sometimes you'll see that it's more congested because everyone wants to use the highway. So that's I'll say it's a mirror version of the brass paradox.
Thanks.
So for the third example involving the routing, even though we further step from the incentivized individual AVs to the coordinate AV formations, we still see this game theoretic taking advantage behavior between mixed autonomy. And the first example here that I want to show you, which is the tolling, which is related to the infrastructure side that currently we have. And the problem is, like, on one hand, we can leverage these infrastructure to facilitate these autonomous vehicles. But on the other hand, sometimes they're not ready. So for example, this tolling scenario, we're very familiar with that. Usually we have a tolling one, which is exclusive for certain parties of the vehicles, which we think should be given like more superior chance to travel the very congested road. And similarly, we also have the regular lanes, which we allow every party of vehicles to join this regular lane without paying anything. And we do consider this very mixed autonomy in the future, where we have human-driven vehicles with high occupancy, and we have human-driven vehicles with low occupancy. By high occupancy, I mean they carry more than one passenger in one vehicle. And in the same time, we have autonomous vehicles with high occupancy and autonomous vehicles with low occupancy. Still, for high occupancy vehicles, they carry more than one passenger. For low occupancy vehicles, they carry one passenger. And compared to human-driven vehicles, they do have a spontaneous and relatively longer headway. The autonomous vehicles, they still preserve a controllable and shorter headway. And perhaps they can be in platoons. So among the four parties of the vehicles, autonomous vehicles with high occupancy, in the meantime, they carry multiple passengers. They can still preserve a shorter headway. So among the four types of vehicles, we think the autonomous vehicles with high occupancy, they are the most capable to increase the social mobility in this case. So therefore, we assume that, but it's actually an assumption that can be relaxed later. That is, we organize all these autonomous vehicles with high occupancy exclusively on tolling one, without any requirement for them to pay the fee. So all of the autonomous vehicles with high occupancy would appear on tolling one without paying any fee. And the other three types of vehicles, they would actually need to choose whether they want to pay a toll to enter the toll lane, to use that shorter delay, more capacity designed by that lane, or they can use freely the regular lane too. And the cost related to the tolling one would be related to one term related to the delay and another term related to the toll. And the cost of regular lane two would be only dependent on the delay itself. So eventually what we found out for this scenario is, right now in this scenario, the lane choice equilibrium is not unique anymore. So previously we can investigate this unique lane choice equilibrium, because then we can make sure that when it happens in the reality, we know the corresponding features, for example, the total delay or the characteristics related to that single unique lane choice equilibrium. But when the case, for example, in this case, the lane choice equilibrium is not unique, and actually it is infinitely many lane choice equilibria, and you are not sure which one the reality would land on. So in this case, it's pretty much chaotic, because all the equilibria that are lying in this set, they have different characteristics and they have different total delay. So what we want to do is, even though we have that chaos, we acknowledge that chaos and we want to investigate how can we efficiently regulate the tolling. So the method here that we propose is that we do kind of rank these different types of autonomous vehicles and high occupancy vehicles. So basically what we compare is their capability of the decision-making parties of vehicles in terms of how much capable that they are to increase the social mobility. And so here we show the result is if, let's say, if the high occupancy vehicles, they carry many more multiple passengers compared to the autonomous vehicles shrinking the headway. If they all transferred into the capability in terms of increasing the social mobility, then the worst case equilibrium would happen when you minimize the number of the number of the most capable party of vehicles on the toll lane, and you maximize the number of the least capable party of vehicles on the toll lane. And correspondingly, the best case would happen when you maximize the number of the most capable party of vehicles on the toll lane, and you minimize the number of the least capable class of vehicles on the toll lane, which is quite intuitive because the tolling is a resource, is an advantage, right? You want the most capable party of vehicles to join the toll lane, to enjoy the advantage, to increase the social mobility. And the corresponding control related to how we can possibly make sure these infinitely many lane choice equilibria to shrink to the best case is very intuitive. That is, we want to design a differentiated tolling scheme. So we give the least toll to the most capable class of vehicles. And we increase their toll until it's the least capable class of vehicles. And in that way, we can shrink the infinitely many lane choice equilibria to the single point of the best case. And similarly, if you have a different rank of the conditions of the capabilities, you can still, even though the best case equilibrium and the worst case equilibrium would shift according to different configurations, but you can still use the very same differentiated tolling scheme by assigning the cheapest toll to the most capable class of vehicles and assigning the most expensive toll to the least capable class of vehicles. And what's good about this framework is we come up with this concept called mobility degree to quantify different vehicles, heterogeneous population vehicles' capability to increase the social mobility. And in that way, you are implicitly compare autonomous vehicles to a new kind of high occupancy vehicles. And currently, we have so many infrastructure that are built for high occupancy vehicles. So with this framework, we can transfer the current ready high occupancy vehicle infrastructure to the future not ready autonomous vehicle infrastructure to save the money, to save the investment, and we can expect the revenue in the short term. So that's a last part of the examples, which is we use the tolling as an example to illustrate the infrastructure support that we need for the autonomous vehicles. And yeah, please. That's actually a very good point. So right now in this work, we assume the demands are the static, which means like every day, they don't really shift the demand among the three decision-making parties. But it's a very critical thing that in the future, when you design the toll, you need to inform the toll to the population. So eventually the equilibrium should change the demand of the three decision-making parties. For example, by encouraging them. I didn't show all the results, but one of the example that we included in the paper that we show that you can design how many vehicles that you think it as a high occupancy vehicles. For example, we call it the occupancy threshold. So you can design that occupancy threshold to induce more people to carpool as high occupancy vehicles. So similarly, we didn't consider that before, but similarly, we can consider a parameter, which is a threshold, like how autonomous a vehicle can be. So we can characterize it as an autonomous vehicle. We can design that threshold to induce more vehicles to use more autonomous vehicles in this scenario. It's good.
I have one more question. When you looked at the equilibria and you switched from kind of the delay to these the capability to the mobility, what was the difference in the equilibrium? I guess you kind of proposed that, but it didn't show it on that
Yes.
that simplex.
You mean
It's
so?
just like the last slide before you
Yeah.
went to the new
Yeah.
section.
So the thing is, like, for the social mobility part, which we do rank their capabilities, it's not involved in the decision-making case. So when people, they're doing decision-making, they only care about the delay, the cost, the delay plus the toll.
Right.
Yeah, but we do use this social mobility as a metric to evaluate the infinitely many choice equilibrium. So social mobility itself is not carried in the decision-making model. It's only as a metric that we evaluate of the results after the decision-making.
So I'm a little confused then. So I thought what you were doing was saying, well, based on some sort of, like toll, setting the toll costs, we're able to move around this, these multiple equilibria points in this space. And then you had one proposal where the highest capability vehicles would have the lowest tolls, and then you had, perhaps I think you called it mobility. The autonomous vehicles would have the lowest tolls. So I imagine that would change based on the costs.
Yes.
More autonomous vehicles. So where did that kind of show up in how does that change the social mobility?
I see. So the point is, if you design the toll, what you change are actually the cost of tolling, right? So therefore, when people, they're making decisions, their decision, so this result, this infinitely many equilibria is a result of no differentiating tolls. So you will have that simplex. If you change the toll, their cost evaluation is different in the game theoretic model. So therefore, the result is naturally not a simplex at all. So it will naturally become the best case if you design the appropriate toll.
Right, but that best case is what you show there, maximum high human-driven, high occupancy vehicles. But then at the very end, you said, well, what if we made the lowest toll on low occupancy autonomous vehicles, right? Like that last slide before you move on to the next section, right here. You show the lowest toll on autonomous low occupancy vehicles. So my question is, where are you relative? Like, I see that the best case is there, but what does that mean for the actual social mobility? If that makes any sense.
If I understand you right, I think maybe the confusion point is you think social mobility is entering in the decision making, like how they.
No. But it's not that, right? So it's, well, based on a simulation where you have these proportions of vehicles in these two different lanes, you can compute some social mobility, right?
Yes.
So you have some simulations where you say, okay, we set these tolls one way and then we set the tolls the other way. What was the end result on how long it took all commuters to reach their destinations across these two different tolling schemes?
Oh, I think so. So we didn't use simulation, but we use it's a model. So we, for example, like the total delay that we calculate in the previous cases in this social mobility is also a total delay, a model driven.
Right.
And the thing is, like, it's shown by the best case, worst case. So the worst case is the one with the largest total delay, which is the least social mobility.
Right. But then you're showing this green point on the simplex for AVLO. And then previously we were showing a point on the simplex for HVHO. And my question is, how do those two compare?
how
does that green point that you have right there compare with this one? This green point?
It's totally irrelevant. Like, because these are showing two cases.
Right.
So no matter which case you have, you can only satisfy one of these conditions.
No, I get that. So that green point that you're showing on this slide and the one that was 2 slides ago, which one has the lower social mobility? It's just a pretty, in simulation. Okay, I can just ask later.
Let's talk after talk, because I don't think I totally capture. Yeah, maybe it's more clear if you actually see the equations. I think that would be a better way. Yeah.
I have a question in the chat from David Ballinson. He said, "It's a very interesting presentation. As a cybersecurity person, I'm wondering if you have thought about adversarial behavior, where participants may not be honest and may try to game or attack the system, or where outsiders may try to attack the system."
Exactly. So the thing is, like, so I think the adversarial behavior right now that we are considering, for example, the taking advantage behavior is also one level of adversarial behavior. But I think the adversarial behavior that is considered in the chat is more related to, like, for example, in terms of communication. So I think in the case, for example, for the very first example, for the Vivian ramps, we want to dictate like 20 vehicles among like 80 vehicles. For example, they need to do this lane change behavior. So communication is the key component there. And when we actually want to implement that control in a certain intersection, we do need to guarantee the cybersecurity, because if someone hacks one of the vehicles, then it will ruin the whole control system. So in that type of follow-up work, we do want to consider the cybersecurity and the adversarial attack related to data and control.
Okay, thank you.
Actually, we can continue the discussion because the talk is important. So yeah, with that 4 examples, I'd like to show is the mixed autonomy taking advantage behavior do persist in different levels. For example, first, when you model these single individual agent until the case where you want to coordinate these controls, and to the case you need system support from infrastructure. And that also shows one of the paths that we can scale up the impact of autonomous vehicles to increase their adoption. And so therefore, in the future directions of my lab is to unlock the potential of autonomous vehicles in intelligent transportation systems and re-engineer the transportation system for seamless integration of autonomous vehicles. And the whole transportation system should be considered as a very coupled, multiple level optimization problem involving both the utility of the users, the interest of the infrastructure operators, the interest of the multimodality system induced by autonomous vehicles like AV operators or human drivers, and of course, the authorities' regulations. And if you're interested in any more specifics related to our work, we can continue our discussion. And also you can scan the QR code. So that's the QR code to my lab. And thank you again for everyone, not only in person, but also on the chat, for attending my talk. I really appreciate it.
Yeah, if anyone in the chat still has questions, you can post them. Yeah, I got another question here. What types of data sets and tools do you use to model roads and develop and test your control algorithms? Like, what tools do you use for your work? I think software.
Okay, so the thing is, right now, for the large scale control, we use the traffic simulator, which is Sumo. Like, we do not have a photo here, but Sumo is actually open source macroscopic simulator where you can configure the different configurations of vehicles, and they do show the macroscopic impact of the whole traffic system itself. And for certain work, there is real world data set, for example, like NGSIM data sets for the ramps, like Los Angeles areas, and for specific simulators, for specific work that are involving like individual control, we also do use Carla.
Carla, okay, thanks. I had a question as someone who's not super familiar with like how the entire like system of autonomous vehicles goes, but I can imagine a future where it's not just like one central directive, but maybe Waymo has their own system, and Uber has their own system.
Yeah.
In that case, maybe a selling point for autonomous vehicle would be we're going to be slightly faster than Waymo.
Yeah.
So is that
that's actually a very good point. So one of another direction of our currently ongoing work is we do consider when we have multiple companies competing with each other on the network, selling their different mobility services. In terms of the game, is a very established game called Cunard Dash game, and the thing is like when we do envision that market scenario would happen in a very soon way. So the eventual combination of those different stakeholders, like different AV companies, they need to compete with each other. But in the same time, they also need to subject to certain regulations from the government. And so sometimes we are very interested in like, is the competition always bad? So maybe sometimes it's not. And but anyway, it's ongoing. So, but that's one of the key directions that we are currently considering. Yeah.
So, instead of acting.
So the strategy itself is very dependent on the certain company, the certain scenarios. But one thing about that is, for example, I do see autonomous vehicles strategy is changing from the very, very conservative side to the more reasonable side. And I think part of the reason, I'm not sure, I didn't ask Wimo, but I do think that's part of because like people taking advantage. Because sometimes I see like if it's not an autonomous vehicle, people would actually play cautiously, but if they see it's an autonomous vehicle, they know they would stop. So they would just do this aggressive cutting. So sometimes playing the most conservative way is not the best for safety. So I imagine the change of the strategy should be also related to the topics in today's talk.
I imagine.
Exactly. Exactly. That's actually the key question that I'm currently interested in. So if you have more autonomous vehicles on the road, then there is more potential that you could make them collaborate. And those collaboration would have an impact on the other human drivers. So that's a very interesting thing.
I guess my question is, if you're trying to optimize something in this area, from my perspective, it would be to reduce or minimize the amount of accidents, right? Not the efficiency of the traffic flow, not how long it takes us to get places. So have you thought about how to understand the highest risks for accidents that are caused by human drivers and how to maybe reduce that and what that would mean? I don't know if there's a lot of studies about those causes. And I recently found that the Department of Transportation invests very, very little in research. I think it was about $2 million a year, which is nothing. So, so can you speak about reducing accidents and if that matters at all in this landscape?
Yeah. So I think here I'm going to comment something personal. So I personally, the topic in my talk is, at the very beginning, I said, the requirements for the safety and the challenge for the technology itself is very highly dependent on how many autonomous vehicles compared to human drivers that you have on the road. So if like you only focus on the current state where you only have a limited proportion of autonomous vehicles, you want them to be like perfectly safe. It's very, very challenging. But if we see a vision of a good benefit to cost ratio and the penetration rate can cross a certain bar in the very near future, then the requirements for the safety and for example, the risks for the accidents would decrease in an exponential way. So I personally think this is the way that we should adopt the technology of autonomous vehicles. And I currently am not an expert in actually investigating the actual safety involving certain individual autonomous vehicles. But I do have this vision that if we don't try that, technology, no technology would be perfectly safe enough if we don't really implement that. So that's my comment, if that helps.
Yeah, if anyone in the chat has a question still, they can, no one's posted yet, but just lay them out.
I guess I know I was asking this question, maybe I can put it a different way. So you have scenarios where you can incentivize autonomous vehicles over human-driven vehicles. And you looked at basically 2 dimensions, the capability, the driving capability of autonomy, which can have like these smaller headways, et cetera, and the high occupancy, which increases the number of people moving through the transit network. We said, well, we can basically modularly charge for these. So my question is it better to have more low occupancy autonomous vehicles in the toll lane than high occupancy human driven vehicles? And like, what is the kind of aggregate impact of those decisions in terms of the actual utility of the aggregate utility, right? And it wasn't obvious to me.
Yeah. I get our point. I think I get if it's a follow-up question to our previous question. I think I get that right now. So the thing is, like, you're right. So currently, for example, in this work, the intention is very good. We try to compare the number of commuters, for example, which is a characterization for the high occupancy vehicle, to the shorter headway, which is a characterization for the autonomous vehicle. The intention is good, but it's definitely not complete. For example, like for the high occupancy vehicles, there is like other benefits, like for carpooling for along the way, right? And for autonomous vehicles, people don't necessarily only carpool for autonomous vehicles. Sometimes they love autonomous vehicles because they have privacy. So to have a complete comparison of the utility of autonomous vehicles and high occupancy vehicles needs to be more systematic than this. But this is a starting point.
And the other question I have is sort of a follow-up to Eric's is, the idea that the central authority would be different per company, but because if the penetration rate of autonomous vehicles increases, then one might imagine that it becomes kind of more fragmented as well. So if there is no central authority, what kind of have you looked at the idea of purely either peer-to-peer or kind of non-coordinated autonomous vehicles and kind of how that might work?
I am. So this is also another maybe personal comment. So the thing is, like, even though there are different companies, in terms of the difficulty for the actual implemented control and communication, I think it's still easier for vehicles to talk to certain infrastructure by sharing only limited information, compared to they need to really communicate their local received information. First, it's partially observable. Second, they need a more strong communication capabilities, and they need the certain penetration rate of the same type of autonomous vehicles from the, let's say, the single operator, right? And they need some utility. If in the case of distributed control and coordination, they need certain utility driven, like why these AV operators want to do this. So to compare all different levels of requirements, I do think in terms of using the potential of the autonomous vehicles, having these different operators, autonomous vehicles talking to a single infrastructure, like a single VRAM zone, or a single very congested intersection, is more reasonable to implement in the very near future compared to the distributed level of control. That's my opinion.
So just to be sure, you think that there might be local infrastructure along roadways which would serve as like a hub rather than kind of a truly central authority that kind of coordinates everything in the city.
Yeah, I definitely. So that's my thought from the practical way. Like, for example, who is driving this initiative and who would benefit? I think that's the most probable scheme that I right now can think of.
Talk about, I think, we want to have like another meeting with you outside of this, but I think because so people have more follow-up questions, 2 people in particular. I think we're basically can end. But so thank you for answering all of our questions and for presenting.
Thank you again for attending.
Yeah.